So next we will discuss interfacing of ADC with 8051 microcontroller. So we'll discuss interfacing of ADC, analog to digital converter with 8051 microcontroller. So let us first see the circuit. What is ADC? It is analog to digital converter. That means it converts an analog voltage like this to an to a digital signal. That means 8-bit representation. So let us take an example. ADC 0804. It's a analog to digital converter. So you are having an ADC. 8-bit ADC will consider. What do you mean by 8-bit ADC? It takes an analog voltage, some analog voltage it takes. So we call it as analog voltage. Can be called it as input V in. With plus, like reference in DAC, we have V in and V in minus. Between this, you have to convert. You have to connect an analog input voltage. So automatically it converts to a digital output D0, D1, etc. up to D7. Now here we have to give V in plus and V in minus. Between them, I have to give an analog input voltage. So usually it is a input voltage. This input voltage to the ADC comes from some sensor. Like example, potentiometer. Okay. So variable signal usually comes to V in plus. The variable signal means potentiometer. Variable voltage comes to V in plus, and the other part V in minus has to be grounded. So like 10k port comes from some input voltage, let us say 5 volt. So potentiometer means it gives variable voltage as analog signal to this ADC, analog to digital converter. Now we need a VCC supply to power this ADC. So that comes from this 5 volt. Then there will be some ground. There are two types of ground. One is digital ground. Another is analog ground, H ground and D ground. Now there will be some chip select signal. In all chip there is some select signal called chip select signal. Here it is CS bar, which indicates that it requires a load to get this chip activated. So we will permanently connect to ground, D ground also. Will permanently connect it to ground. Okay, so this is grounded. Now we have to give a clock signal to this because this has to be synchronized. So clock R and clock in, these are the two pins which we have to supply the clock. So this way we are connecting the clock. Now there are some control signals to control this ADC, which are read bar and write bar. So as the name indicates, read bar, it takes input. Write bar means that is also it takes input for some controlling. One is to do the conversion, because it has to do analog to digital conversion. When it has to do analog to digital conversion, when microcontroller says please do analog to digital conversion, so that starting of that conversion is initiated by giving a signal WR bar. Now once the completion is over, once the completion of the conversion is over, there is a control signal, there is a control signal which informs the microcontroller that conversion is over. That is, that signal name of the signal pin is INTR bar. That means once the conversion is over, this will give an information to microcontroller. That means this is the output signal. This gives an information to microcontroller that conversion is over so that you can read. So this read is the control signal which allows the microcontroller to read the digital signal from ADC. These are the control signals. Now D0 to D1, we will connect to some port of the microcontroller. Let us say I am connecting it to P1 port. So P1.0, P1.1, etc. up to P1.7. Now remember, ADC converts analog signal and converts to digital and gives to microcontroller, and microcontroller takes it. That means reads it. That means P1 is the input port for microcontroller. Now similarly, after the conversion is over, ADC is informing microcontroller. So I will use some port bit P2.7. Through P2.7 is the input port bit for microcontroller, and it gets signal from INTR bar of ADC. Now these two are control signals to start the conversion and to give information to that I want to read it. So these are P2.5 and P2.6 we'll use. So P2.5 and P2.6 we'll use. So P2.5 give the information, P2.5. So P2.5 I am connecting to read bar. Okay. P2.5 I am giving to read bar. Whenever microcontroller wants to read the digital data from ADC, it gives a signal through P2.5 to read bar, so that this will allow reading. And write bar means it is the information given by microcontroller to start the conversion whenever it wants. So that I am connecting P2.6 is the control signal given by microcontroller to write bar, so to ask for the conversion to happen. So this is the connection diagram. This is 8051 microcontroller. Now sequence of steps it has to perform for a conversion is, whenever microcontroller want to read a digital signal from ADC, first it has to tell ADC please do the conversion. So that is done by means of a write bar. Then it starts converting. After conversion, ADC will inform through INTR bar to microcontroller that conversion is over. After that, microcontroller has to give information to ADC to allow reading. So first it has to initiate, microcontroller has to send a signal through WR bar to give an information to the ADC that start conversion. So it starts converting. After end of conversion, through INTR bar, ADC will give information to the microcontroller that conversion is over. Thereafter, microcontroller has to give a read bar signal. Through that, it has to give information to the ADC. So information has to be like this: microcontroller to ADC, first to ask to start the conversion through WR bar. Then it starts converting. After conversion is over, it informs microcontroller through INTR bar that conversion is over. After that, microcontroller will tell through read bar to the ADC that I want to read. This is the steps. So let us do the timing diagram. Very, very important. How the control signal. According to that, you have tried the program. So there will be a CS, I mean a clock type of signal, permanently grounded also okay. So this is a chip selector. Now whenever this, this has happened, CS bar has happened. CS bar means 0, active load time. Microcontroller has to give information to start the conversion. So it's somewhere here. When the CS bar is down, it should happen. So WR bar, when this is 0 till this moment, it is 0 means it gives an information to start the conversion. To start the conversion. So it gives the information. After that, for the next cycle, you have to make it 1. So here the start of conversion happens. So whenever the WR bar is 0, the start of conversion can happen. If this is also 0, then immediately after giving that signal, starts of conversion, for the next cycle, it can go to high, and in the next cycle only, it has to make a low to start again conversion. Okay. Now, after start of conversion, it starts converting. Once starts converting somewhere, INTR, if it is end, if the conversion is over, INTR will go low. Initially it will be 1. This will go low when this is also low, means that end has happened. End of conversion has happened. End of conversion has happened. Now, after conversion is ended, microcontroller can read by giving a read signal. How to give the read signal? Initially, it should be high. After end, means somewhere after end, it goes low to say that I want to read. Okay. After this point is over, your D0 to D7, after this point is over, D0 to D7 will contain digital bits which goes to the microcontroller. This way you have to program. First send a signal through write signal, that WR bar signal that starts the conversion, and get ready. That is how, by making 0 and then making 1 for the next cycle. Then it will wait for an interrupt signal to come. So INTR bar goes low means that conversion is over. This here is the end of conversion. After that, the microcontroller will give issue read bar signal low so that it can read through D0 to D7. And for the next cycle, after reading is over, after some time, it has to go high again for the next. So that for the next reading, it has to go low. So this is how you have to make the program. So let us start the program. You remember the connections. Wherever we have connected, you have to remember. So first is P1 port is expected to carry digital data coming through D0 to D7. So that means P1 is an input port. So you have to configure P1 as an input port. So how will you make P1 as an input port? You have to give FF to it. So this declares P1 as an input port. P1 is an input port by giving FF to it. Now, there is one more port bit which is input port bit. That means INTR bar is giving signal to microcontroller that conversion is over. So P2.7, a single bit, is also an input port bit. So set bit P2.7. This will configure P2.7 as input. P2.7 is input port bit. That configuring will be done. So after configuring, you have to give a control signal WR bar. WR bar is the control signal to start the conversion. So you have to give what? Low signal. So clear WR bar is connected to P2.6. So it starts converting. Once it starts converting, immediately you can get ready for the next cycle. Once again, it have to clear for the next data. So before clearing, you should do set bit immediately. That means it will first make P2.6. I mean right bar low so that it starts converting, and once it's this one our ADC starts converting, uh, that starts converting signal need not be maintained. So you can make it opposite so that for the next time again you can make it low and starts converting. Okay, so it starts converting. So ADC is converting. Now after conversion is over, ADC will inform microcontroller that conversion is over through which signal? INTR bar. INTR bar is connected to P2.7. So as long as P2.7 low means conversion is over, high means jump on bit. Jump on bit means bit is high. Jump on bit means bit is 1. When it is high, conversion is not over. So you have to wait here only. Wait here only. What it means? Jump on bit. Bit means a bit is 1. So as long as one conversion is not over, remain there itself and wait for the conversion to get over. Here means no bit. No bit means INTR bar has become 0. INTR has become 0 means here the conversion is over. Conversion is over. Once conversion is over, microcontroller should give signal to read it. So read is connected through P2.5. So read bar it is. So to say that I want to read, first you have to clear P2.5 because P2.5 is connected to read bar. So it starts reading. It starts reading means it P1 starts reading that digital input. Digital input. That means digital output of ADC comes as digital input to microcontroller through P1 because we have connected P1 to D. So microcontroller starts reading means that D0 to D7 will come to P1 to P7. So it is available in P1. Take it to accumulator. It is coming through. It is reading through P1. Take it to A. Then this digital data will be 11111111. So you have to convert it to hex or ASCII number because as a bit you cannot display anywhere, no. So you have to, if it is 11111111, that means it has to be converted to FF. So some conversion has to be done. So you call a subroutine to convert that binary bits to some format, hex or ASCII, etc. So A called, that we will call the name as subroutine as conversion. After conversion, no, the value FF has to be put to some display like LCD display or something. So for that I will call a subroutine called display. Display that value whatever received. After display, that means one data is completely read. You have to be ready for the next reading. Now it is cleared and it's already given information for reading. So reading has happened. You have to set bit P2.5 because by clearing P2.5 it has given information for reading. After reading everything is over, you can reverse it, set bit P2.5 so that no more reading is required. Next data only, whenever it comes it has to clear and read. Okay, so set bit P2.5 and S jump, this process has to continue. S jump back. Back going to what? For the next conversion you have to give the signal. Correct. So that back is going to here. Why next going to here? So after one conversion is over and read and displayed, you have to give information for the next conversion. Again, you have to convert next value. So next value conversion starting from here by issuing a start of conversion signal through P2.6 or WR bar. So this is the program. Clear?